Hello everyone. For the video of today we got this bad boy of a proof right here. Okay, so firstly, what does it say? Okay, it says r to the power of n minus 2 is always less than f index n, which is less than r to the power of n minus 1 for all r in n, and when n is greater than or equal to 3. This may look like utter and complete bullshit, but R here refers to the golden ratio, and F is the Fibonacci sequence of the index n, and this Fibonacci sequence that we're counting, we're using here, is the one that starts with 0. No, I'm sorry, not the one who starts with 0, the one that starts with 1. Sorry, I need to think a bit. Okay, so it goes 1, 1, 2, and then 3, and 5, and 8, and yeah, so on, towards infinity. And exactly, and the golden ratio, what is that? That is 1 plus the square root of 5 over 2. Before we start with all the induction hypotheses, I want to give you a property of the golden ratio, and it's the fact that 1 plus the golden ratio is equal to the golden ratio squared. And this is thereby how you get the golden ratios, by solving this quadratic equation. So yeah, that was this. Okay, so now we need to start with the induction. So we're going to start by showing the first two cases, when n is 3 and when n is 4. Okay, so when n is 3, what do we have then? We have that r to the power of 1, which is then just 1 plus the square root of 5 over 2, is less than f, the third Fibonacci, which is 2. And this thing here should therefore also be less than r to the power of 2, which is then 1 plus r, which then just is 3 plus the square root of 5 over 2. And to prove this, we can just toss a bunch of shit around, and well, yeah, we can just multiply by 2 everywhere, and then we'll subtract some things. Okay, so we'll have that.
Okay, 1 plus square root of 5 is less than 4, which is less than 3 plus the square root of 5.
And what can we do here? Okay, firstly we can look at this inequality here, which we can just, okay, so we would then subtract by 1 and square both sides, and then we would get that 5 is less than 9, which is obviously true. And for this inequality, we would just subtract by 3. Okay, so 1 is less than the square root of 5. Square both sides, 1 is less than 5. That is quite obvious. So that was the first case. Okay, n is equal to 3. That absolutely works. And now I need more space. So give me un momento. Okay, now I'm back. By the way, please share in the comments which accent you think I should have in my next video. I can do a bunch really poorly. Anyway, okay, so that was n3. What about n4? Okay, so then we have that we want to show that r squared is less than the fourth Fibonacci number, which is then less than r to the power of 3. R squared, as we knew from before, was 3 plus the square root of 5 over 2. And then this is supposedly less than the fourth Fibonacci number. What is the fourth Fibonacci number? That is 3. What the fuck? Did I just... Okay, I'm having a stroke. Damn. Okay, that is a 3. Jesus Christ. And then r to the power of 4, no, sorry, r to the power of 3, that plus, well, yeah, plus with the golden ratio. So what is that then? Okay, so then you just add them up. So then you would get a 4 plus 2 square root of 5. So then the 2's cancel out. So you get a 2 plus square root of 5, if I'm not incorrect. And to prove this, I'm not going to really write it out. We can do the same thing here. I'm just going to talk instead. So regarding this inequality, what would we do here? Okay, we multiply by 2, so we get 3 plus square root of 5 is less than 6. Subtract by 3, okay, so we get the square root of 5 is less than 3, which is clearly obvious. Square both sides, 5 is less than 9. Check. Done. And then for this one, subtract 2, 1 is less than square root of 5. Square both sides, we get this exactly the same thing as before. Nice. So now, what do we do now? Well, since we're looking for, we have n and we have, or sorry, in total inequality, we have fn r to the power of n minus 2 and r to the power of n minus 1, right? Okay, so we have both n minus 1, and n minus 2. That calls for 2 induction hypotheses. So what should we do therefore? Okay, so we say that our k is equal to 4, and because we have shown that this thing works when n is equal to k, which is 4, and the k minus 1, we therefore are allowed to make our induction hypothesis that it works when n is equal to k and k minus 1, and we shall then prove it when n is equal to k plus 1. So we therefore assume that r to the power of, I'll start with k minus 1, so therefore we have k minus 1 minus 2, so that's k minus 3 is less than f of k minus 1, which is less than r to the power of k minus 2, and the same thing where n is equal to k, so we have that r to the power of k minus 1 is less than f k, which is then less than r to the power of k minus 1, and we want to show that r to the power of k minus 1 is less than f index k plus 1, which is less than r to the power of k. Okay, so how do we do this? We use the property of the Fibonacci number. So we know that Fibonacci of k plus 1 is equal to Fibonacci of k plus Fibonacci k minus 1, right? That's the definition of the Fibonacci sequence. And here, now we can use our induction assumptions. So firstly we look at this inequality, then we have that is less than that. And then we can start by this side and use these inequalities. So we have that fk plus fk minus 1, what is that? Fk is, so now we want to prove that it's less than something. We want to prove that this thing here is less than, well, okay, fk is less than r to the power of k minus 1, and fk minus 1 is less than r to the power of k minus 2. So therefore we can just sum these up and say that it's less than the sum. So less than r to the power of k minus 1 plus r to the power of k minus 2, right? And now what do we do then? Well, we utilize the facts as we did the fun fact or the handy trick with the golden ratio as we used before, the fact that 1 plus r was equal to r squared. So what is this here? This is r to the power of k minus 2 times r plus 1. And what is r plus 1? R plus 1 is r squared, and therefore the 2's cancel out, and this is just r. Okay, so we've done that part, and doing this inequality is extremely similar. Instead, you just switch out that, okay, this is less than that, and this, yes, exactly, this is less than that, and this is less than that, and then you utilize the same trick, and everything just goes away so nicely. And yeah, I don't feel like doing it, so I'm just gonna say proof concluded, shut the fuck up, and go to sleep. Good night. Have a good one. Bye bye.